This lesson is on something called Ramsey Theory. It's kind of at the intersection between combinatorics and graph theory. It's named after Frank Ramsey. I have a little blurb about him on the top here. He was a British philosopher, mathematician, economist who made major contributions to all three fields before his death at the age of 26. So he died quite young from liver disease, which is unfortunate because he made some significant contributions in his short life. This presentation is partially from Notebooks LM. You can see that on the bottom of some of the slides, but some of the slides were not usable, and I deleted those and I added some of my own information. So just to let you know where the source is, basically two places, Notebook LM and myself. The title is called Order and Chaos, and you'll see why that applies here in a bit. So we have a quote here. This is from a mathematician, Motzkin. He's an Israeli American mathematician, and his quote is, "Complete disorder is impossible." So again, hitting at the title of the presentation here, and we'll see that first in this example here. This is called the party puzzle. Imagine you invite 6 random people to a dinner party. What we're going to prove later in this lesson that for sure among any 6 people you're guaranteed to find either a group of 3 mutual friends or a group of 3 mutual strangers. So this is kind of an inkling of the fact that if you take a graph of relatively modest size, you can be guaranteed of certain structures existing in the graph, and this is one example of it. This is a bit of a repeat if you've seen some of my previous lessons on graph theory. It's just showing how to map the puzzle to a graph. So we have the vertices representing people, vertices of a graph. Then the edges represent relationships. Now we have 2 types. We have friends, which we'll do in blue, and then we have people that don't know each other, and we'll show that as red. So for example, if we look at this vertex here and this vertex here, it's showing that these 2 people are strangers. And you can see that we have a group of 3 people that are mutually unknown to each other. In other words, they're 3 strangers. And that was one of the 2 conditions of the party problem, that if you have 6 people, you're guaranteed to have either 3 people who are strangers to each other or 3 people who are friends. In this particular example, we have 3 people who are strangers to each other, but we don't have any group of 3 people that are mutual friends. Eventually we'll prove this, but it'll take a bit of work to get to that. So I'm just kind of building up to the solution. The explosion of connections. A complete graph, K sub n, which I've talked about in previous lessons, is a network of n vertices where every single node is connected to every other node. So I have K 3, 4, 5, and 6. And the point here is that as you get into more complex graphs, there's certain guarantees of structures existing in those graphs. And that one example was this party problem that we introduced earlier, where we said if we have 2 different types of relationships between the vertices, then there's at least one case where you have 3 friends, mutual friends, or 3 mutual strangers. Now, of course, we could change what the relationships are, but the idea is it's binary. You can have 2 people who are either strangers or friends. So what I'm going to do in the next few slides is talk about the 2 variations of what's called the Pigeonhole Principle. We're going to need that to actually solve our party puzzle. I've taken the following few slides from a previous lesson, so I recorded it using a different microphone. My voice sounds a little bit different, just to let you know what to expect. And that's not from Notebook LM. It's some slides I created earlier. We're going to, in particular, use the second Pigeonhole Principle to solve part of our party problem. The pigeonhole principle goes as follows. If each item in a set of n items, call it set 1, is to be associated with one item in another set, which we'll call set 2, where set 2 has m items and n is greater than m, then at least one item in set 2 must have more than one item associated with it from set 1. So this seems fairly obvious, and it comes from pigeons, so just giving concrete numbers here. If you had 10 boxes for pigeons and you had 11 pigeons and you tried to associate a pigeon with each one of the 10 boxes, obviously you're going to have one box that has more than one pigeon in it. So I have another example here similar to what I just said. This seems terribly obvious. For example, if you put 10 balls into 9 boxes, then clearly one of the boxes must have 2 or more balls. This principle is nevertheless very useful and is not always so obvious as to when it can be applied. So I have an example. Suppose that you have a collection of many red marbles, blue marbles, green marbles, and white marbles in a box. What is the least number of marbles that you need to retrieve from the box while not looking? So you're randomly, putting your hand in the box, and you're blindfolded, for example, and you want to be sure of getting 2 marbles of the same color. So I'll give you the answer to this on the next slide. At first glance, it's not clear how this problem relates to the pigeonhole principle. At least for me, it really wasn't clear when I first saw this. After some thought, one approach is to let the 4 colors be the pigeonholes. So m is equal to 4. We're being asked to find the smallest number n, such that we're sure to draw 2 marbles of the same color. So one can view set number 1 as the number of draws. The smallest value of n to ensure the desired result is 5. We can also look at this as a worst case analysis. So you have this large container of marbles and you want to get 2 of the same color. So what would be the worst case? Well, you would get a red, a blue, a green, and a white in the first 4 draws, and then the 5th draw you have to draw one of those 4 colors, and that would guarantee you to have 2 of the same color. So of course it could happen sooner, but this is stated in terms of worst case analysis. This is the generalization of the pigeonhole principle that I mentioned, and we'll use that to solve the party problem. So if each item in a set of k times m plus 1 items, we'll call that set 1, is to be associated with one item in another set, we'll call that set 2, that has m items, then at least one item in set number 2 must have k plus 1 items associated with it. So the set 1 are sort of the balls or the marbles or the pigeons, and set 2 are the containers. And we're saying if we have k times m plus 1 items and we distribute them into our set number 2, which has m containers, then one of the containers has k plus 1 items. So maybe an example make this a little bit clearer. Let set number 1 consist of 3 times 10 plus 1 equals 31 balls. So I'm just breaking out here. K is 3, m is 10. And set 2 has 10 containers. The generalized pigeonhole principle tells us that at least one of the containers must have k plus 1 or 4 balls. So again, we can do sort of a worst case analysis. We have these 31 balls and 10 containers, and we want to try to avoid having 4 balls in any one container. So the worst case would be, or depending on your perspective, the best case would be to put 3 balls in each of these 10 containers, and we still don't have 4 balls in any one of the containers. But when you decide where to put that 31st ball, you have no choice. You're going to have one container that has k plus 1 or 4 balls in it. Here's a variation on our first example with the marbles. but this time determine at least number of draws that are needed to ensure at least 5 marbles of the same color. So if you want to give this a try, you might want to pause here, and I'll come back on the next slide and give you the solution. Using the pigeonhole principle, generalization number 1, we want k plus 1 equal 5. In other words, we want to be guaranteed to have 5 marbles of the same color. So that implies that k would be 4. Further, as before, m would be 4. That's the 4 colors. That would be our 4 containers. So k times m plus 1 is 17. So the answer would be 17 draws from our large container of marbles would be required to ensure to have at least 5 marbles of the same color. So that's kind of more of a technical way of looking at it. And the other way is more of a worst case analysis. What's the least number of balls you need to draw to be guaranteed of having marbles of the same color. And so you can see here, the worst case would be that you get, in your first 16 draws, you get exactly 4 green, 4 blue, 4 yellow, and 4 red. And then on your 17th draw, you're going to have to pick a marble of one of these 4 colors. I showed yellow here, but it could be any of the 4 colors. So that's the answer is 17. And just to make clear, the probability of that happening is not high, right? You wouldn't expect that to happen, but this is to be guaranteed to have at least 5 marbles of the same color. You need to pick 17. And we're going to use this to solve our party puzzle. So back to the party problem. I want to solve that by isolating one particular person in the group. We'll call that V1 or node V1. And then from the generalization of the pigeonhole principle, we can let the colors be the second group, M equal to 2, since we have 2 colors. And then the km plus 1 is the number of edges. That would be 5, right? Each person, this particular person, V1, would have 5 possible relationships, either a friend or a stranger. So that's 5. And then we can just plug the m equals 2 into here, and that says k equals 2. And then the generalization number 1 of the pigeonhole principle says that you're guaranteed to have 3 edges or 3 colors of the same. Or we can look at it just from a worst case analysis. You have a person here, and that person is either a friend or a stranger of these other 5 people, and you have to have at least 3, either 3 friends or 3 or be stranger to 3 people. I'm showing the case here where you have 3 friends. Now you could have 4 or 5 friends, but the idea is that you have at least 3 friends, or going the other way around, you have at least 3, you're a stranger to at least 3 people. The cases are symmetric, so we'll solve the problem looking at it with this case here, where V1 is friends with 3 other people. Then there's 2 subcases where we'll find the trio of friends, or we'll find the trio of strangers, and I'll show you that on the next couple of slides. So the first subcase is where the friends of V1, in other words, V2, V3, and V4, at least one of them is friends with each other. In other words, if any pair from V2, V3, V4 are friends, then we have a trio of friends. And I'm just showing you one example here where V2 and V4 are friends, and you have this trio of friends. It could have been V2 and V3, and then you would have this trio of friends, or V3 and V4, and then you would have this trio of friends. But in any case, if any 2 of these are friends, then you have a trio of friends, which would include V1. Then there's the other case where you don't have any pair of these 2 being friends. In other words, they're all strangers, and that's the second subcase, which I'll show you on the next slide. So this subcase is even simpler. It's the opposite of the previous subcase where V2, V3, and V4 are not friends. They're strangers to one another. But then you have a red edge, right? It means stranger between these three, and so you have a trio of strangers, which solves our problem. The other super case, the up front, is where you would have V1 being a stranger to three others, but it's completely symmetric to what we just did here. We would just be switching red for blue and blue for red, so I'm not going to repeat that. So what we just saw is an example of a Ramsey number. We have this notation here. It's basically saying that if you have a minimum of n vertices in your graph, or n people to relate it to our problem, then you're guaranteed to have S of certain type of relationship or T of the other type of relationship. In our case, it was blue, three blue, three mutual friends or three strangers out of the six. But these numbers can be different. It's the same idea. You have these different characteristics, and you want to be guaranteed of having one type of characteristic, a certain number of one type of characteristic, or a certain, or T of the other type of characteristic. It turns out these are extremely difficult to compute. I'll show you that on the next slide. We did the easy one, or one of the easier ones, but most of these are not known, even for relatively small numbers for S and T. There's no known solution yet. So here's a table of the Ramsey numbers. So our S and T I have here on the sides here of our table. So we did this one here, S and T equals 3, and so that was 6. For S equal 3 and 4, so in other words, 3 of one type, 3 red and 4 blue, you have to have at least 9 vertices to guarantee one or the other. For 4 red and 4 blue, you would need at least 18 vertices to guarantee one or the other happens. And then the other case that's known as 4 and 5, that's 25. Now that's pretty complicated. When you think about it, you have a graph of 25 vertices. There's a huge number of connections already. When you go to 5 and 5, there's no known answer yet. The range is between 43 and 48. This is from Notebook LM. You'll see a little bit later, I went to Wikipedia, and they have slightly updated numbers on these ranges. So the ranges are, with a lot of hard work, the ranges of possible solutions for the n, least number of vertices you need, is getting tighter. And then for 6 and 6, you have this range here. And again, I think the Wikipedia article has slightly smaller range here, which I'll show you in a few slides. This is kind of interesting. Thought it was humorous. It came from Notebook LM. The Hungarian mathematician Paul Erdős, who also worked in this topic, had this statement about the alien ultimatum. He said, suppose an evil alien would tell mankind, either you tell me the value for R55, and we saw that we don't know what the exact value is yet, or I will exterminate the human race. In that case, he said it would be best in this case to marshal the world's best minds and fastest computers to try to compute it. So he kind of thought it was, and he died in 1996, so he probably made this statement a few years before that. And he thought it was maybe possible if we just got everybody behind trying to solve this problem. That's how hard he thought it was. And he said if the aliens asked the same, made the same threat, but they asked for R66, basically he's saying there would be no hope, and we best try to destroy the aliens before they destroy us. So that's just the opinion of a very prominent and famous mathematician, that the problem is not likely to be solved. Again, this was over 30 years ago, and in fact, we've just made a little progress in narrowing the range, but not getting the exact solution yet. We may not in any time soon. And granted, computers are much more powerful than they were 30 years ago. So I got this from Wikipedia, this table here. So the table I showed you earlier, I believe it went up to 6 and 6. These numbers are a little bit tighter. These are the ranges where we don't know the specific solution. And you can see that people have done work proposing ranges for different numbers here, 8 and 8, 9 and 9, even for 10 and 10. The minimum number of vertices in your graph are bounded by these two numbers here, but that leaves a lot of leeway as to what the optimal solution is. So you may want to take a look here. I gave the source of the Wikipedia article. I also gave the birth and death years of Paul Erdos. And as I mentioned on the previous slide, he made his statement about the alien threat over 30 years ago, and we've just made a little bit of progress in tightening the ranges here for 5, 5 and 6, 6. I have a couple of exercises for you to try. These are not Ramsey theory problems. They're just pigeonhole problems. And this is similar to something you've seen before, but you might want to give this a try. So the scenario is you're in a pitch black room. On a shelf, there are 10 pairs of shoes all mixed together. What is the absolute minimum number of individual shoes you must blindly pull from the shelf to mathematically guarantee that you have a matching pair? So if you want to try this, pause the video and then I'll give you the solution on the next slide. So the answer is 11, and it's basically a worst case analysis. You can imagine you have 10 pairs of shoes, and if you got very unlucky, you could pick one shoe from each pair on your first 10 draws. I understand that probability is almost zero that would happen, but again, you want to be guaranteed of having two shoes from the same pair. And so on that 11th selection, you have to make a pair since you've already depleted all the one of each of the pairs of shoes already. So that's, I think, fairly straightforward. I have another problem for you in the next slide. Let's have a look at that. This one actually completes the solution to the party problem. What we showed was that if you have 6 vertices, you're guaranteed of having either 3 red or 3 blue edges. The question is, could that be guaranteed with say only 5 vertices? And that's what the problem is here. So I'll just read what I have here, or what Notebook LM has here. We proved earlier that R33 equals 6. This means 6 people guarantee a monochromatic triangle. In other words, a triangle of the same color, basically 3 people, a trio of people who are strangers or friends. But to prove the absolute minimum is 6, we must prove that 5 people is not enough. In other words, R33 is greater than 5. The question is, can you color the connections between 5 nodes using only blue and red so that no triangle of a single color is formed? And then that would prove that you need 6 in order to guarantee either 3 red or 3 blue. Okay, if you want to give that a try, go ahead and pause the video and I'll come back and give you the solution on the next slide. So here it is. You can do the edge here along the outside, make that red, and then all these internal edges blue, and you notice there's no triangle here of one color. And so that proves you can't guarantee it with 5 vertices. You need 6. So that's what you need to do in these more difficult cases. You need to show that that's the minimum number in order to prove that you have a Ramsey number, an exact solution. I have a concluding slide here. It's just the general idea that if you have a graph with a lot of vertices here, it's impossible to avoid some type of internal order. We saw the case where you have 6 vertices, you have either 3 red or 3 blue edges that make a triangle, but there's all other types of patterns that are guaranteed to appear when you have a larger number of vertices. The problems are very difficult. You can see there's only exact solutions for a very few number of cases. And this has been known for quite a long time. This problem is, for many decades. Okay, so I think this is, for the time being, my last lecture on graph theory. I'll be working on some other videos on different topics. So if you like this, please give it a thumbs up and stay tuned for my future videos.